Let's start. I'm going to try to finish this chapter today if we have time. And so we were in section 2, Bogoliubov transformations, and remember that here what I did was to compare two quantizations that you may choose. So we can choose to decompose the space of solutions in a positive and negative norm, or you can choose a different decomposition. Normally, at the practical level, we choose a decomposition by choosing a basis of this space, and this is just the complex conjugated, and you can choose another basis, different basis. And our goal here was to relate both quantizations. This is a positive norm basis, and the trick was to realize that we can always find complex coefficients such that we can use the basis one to write the phi 2 for some complex coefficients. If both bases are normalized, they have to satisfy this condition. And from these relations, these guys are Bogoliubov coefficients, and they encode the information, the relation between both quantizations. We found that one can write the annihilation operator 1 as alpha A2 plus beta conjugated A2 dagger, and the same for similarly for A1 dagger. We can invert the relation, and we also saw that the state. So therefore, we have therefore two different vacuum states. Normally, the vacuum that we get are different from each other if the beta coefficient is different from 0. And we also saw explicitly how to write this state in the Hilbert space, in the focus space of the quantization 1. And it was normalization factor 1/2 beta star alpha star A1 dagger vacuum 1. That's it. And I want to make a comment here because last day I was going ahead of my head and saying that, you know, if you expand the exponential, this is a state which has vacuum plus 2 particles plus 4 particles, and it was saying that the particles are entangled with each other, and this is what happens in quantum field theory. But here, that is just simply not correct in this case, because here, we only have one system. When you talk about entanglement, what you have to do is take the Hilbert space, separate it in 2 subsystems, take the state, and trace over one of the subsystems, and see if what is left over is a mix or a pure state. But here we only have one system, so it is not really proper to talk about entanglement of quanta, because we only have one type of quanta. When we are in quantum field theory, we have one type of quanta for each k, and then here I will have k and I will have minus k, so I can talk about entanglement between quanta going in this direction and in this direction. And I was thinking on that when I was talking about it.
But right now we just have something that's excited twice.
Twice, exactly the same quanta, so it doesn't, there is no way to talk about
that is not too entangled.
Right, it's not really proper to talk about entanglement because we cannot really divide the system in 2 subsystems. So I apologize, forget about what I said about entanglement. I was thinking in quantum field theory because this is the way that we normally write the things. In that case, one will have entangled quanta. But the main point is that this vacuum 2 in the focus space 1 is not vacuum at all. It is a state full of particles with precisely that structure. And last thing we did was right. So last thing we did was to say that one can compute how many quanta the vacuum 2 has in the focus space 1. So what is the expectation value of the vacuum 2 with the number operator 1, and we saw that this is just beta squared. So beta squared has the information of the average number of quanta 1 encoded in the vacuum tube, and vice versa. So we stop here. So to finish this section, I want to make a few comments which are kind of important. So now it's new material. So comments. The first comment I'm gonna make, I repeated it last day 50 times. So is that the lesson here that we are learning here is that the notion of vacuum and quanta are basis dependent. So in an arbitrary time-dependent situation, what we mean by vacuum, or so the notion of vacuum and quanta do not have an objective physical meaning. It's just a basis-dependent statement. It's as basis-dependent as saying that this vector has some value for the x component. That depends on what you mean by x component. That doesn't mean anything in general. Exactly happens with the notion of vacuum and quanta.
If I'm sitting here in my own laboratory and I want to measure how many particles I have, do I have one preferred choice of basis then? Or?
No, you can choose.
Okay, so I can choose other bases, but that seems to seem, I get the notion that I may get different measurement results on my choice of basis.
Depending what your measuring apparatus is.
Oh.
So your measuring apparatus is going to measure quanta characterized by the phi 1 solution or by the phi 2. Depending on what your apparatus is, you will measure some number of quanta or a different number.
Okay.
So it's completely a basis-dependent statement in arbitrary time-dependent situations. So, second comment, is a comment on the comment. So, what I want to say here is that comment 1 seems contradictory with what we saw in chapter 1, for instance. So in chapter 1, and I already mentioned this comment last day. In chapter 1, we saw that chapter 1 was in the time-independent situation that there is one state that we call the vacuum there, which is the ground state of the Hamiltonian. So can we use the same criteria here to select a preferred vacuum state? So can we use this strategy here? I mean, take the Hamiltonian, diagonalize it, so look for the eigenstates, and take the state with lower eigenvalue, so that is the ground state, and call that the vacuum. So the answer is, unfortunately, no in a time-dependent situation. So here, the Hamiltonian is time-dependent, therefore energy is not conserved. So you can already imagine that if energy is not conserved, we are going to have troubles in finding eigenstates of the Hamiltonian at all times. So to see that explicitly, you can write the quantum Hamiltonian. So the quantum Hamiltonian reads. So this is something that I want you to check. So this is my first present today. I give you the solution. This is 1/2 mass. Maybe I should write it there because I don't have space here. So quantum Hamiltonian, 1/2 mass, and now I have a bunch of terms. I have a term A dagger with coefficient phi squared omega of t square phi square plus a term. I said a dagger, but I meant a. Now I mean a dagger. A dagger is just the complex conjugated of this term, square minus omega of t square phi square, everything conjugated, all the parentheses. And now I have one more term, which is this square plus this square multiplying a dagger a with a factor 2 plus h bar. This parenthesis multiplies this. Where phi and phi star are an arbitrary basis of the space of complex solutions. Of course, phi with positive norm and phi star with negative norm, as usual. So this is the form of the Hamiltonian. So if you remember what we had in the time-independent situation, we only had the last term. We didn't have any term a dagger, neither a.
Is that phi dot squared in the a dagger parenthesis?
Yes.
Okay, there's not.
Phi dot square. In that case, what happened is that we choose, remember we choose the basis e to the minus I omega t divided by the square. So if you take time derivative, this brings down I omega. If you take I omega squared, you have minus omega squared, and this parenthesis was 0, this parenthesis was 0, and this parenthesis was just omega squared, 2 omega squared. So in that situation, all the first term and the second term was 0, and we only had the third term. But now we have the three of them. So for a generic basis, this term is not 0. We don't have solutions with positive frequency and negative frequency. So we have those terms. So therefore, you can see that the vacuum is not an eigenstate of the Hamiltonian. If this Hamiltonian acts on the vacuum defined by these modes, this is going to kill the vacuum, but this is going to excite it. So from here, you're going to get a two-particle state, and this is just the number operator. So you will get the vacuum from here. But the result will be a combination of a two-particle state and the vacuum. So the vacuum for an arbitrary choice of positive and negative norm solutions is not an eigenstate of the Hamiltonian. So now the question, can we choose?
I mean, but there will always be some minimum energy state, right?
Right. So the statement is, can we find phi and therefore phi star such that the associated vacuum is an eigenstate of the Hamiltonian at some time t naught. So fix the time, and let's see if at that time I can find an eigenstate of the Hamiltonian with the minimum energy. The answer is yes. Yes. Do you guess how?
Take expectation and then derivative equal to
At that time, we can choose our solutions to be the time independent among the.
Exactly. Choose solutions. There will be whatever solutions such that at t equals 0, they have initial data as if they were positive frequency nodes. 1 over root square. I don't have to write the phase because the phase is unimportant. The frequency at t0, m, and minus I omega at t0. Remember, we already discussed that this initial data produces solutions. There is only one solution with this initial data t0. which have norm equal 1. And you can see that if you plug that here, at T naught, this term is 0, and this term is 0, and you don't have the last term. So the associated vacuum, so because we have a state which is a basis of S plus, so we have a basis of S plus and S minus. We have therefore a vacuum, let me call it T naught, is an eigenstate of H naught, H at T naught with minimum eigenvalue. So we have succeeded in finding, at a given time, a state which is the ground state of the Hamiltonian. But what is the bad part here?
They no longer remain in the
Right.
this form.
Right. Because there are no solutions with positive frequency. At any other time, T prime, the state will not be positive frequency mode. So this term and this term will not be 0 at a later time. That at a different time, this state will not be, I was calling it T naught, will not be an eigenstate of the Hamiltonian, unless omega of t is constant. So the best we can do is to find an instantaneous eigenstate of the Hamiltonian. But there is no single state which is the ground state of the Hamiltonian at any other time.
Can you find like with function of time as function of time?
Right, but you will find a one-parameter family of states. So today the ground state is something, but tomorrow you have to change the state because that state is not the ground state anymore. Essentially, the time-dependent situation is giving energy to the system, and the state is not longer the ground state. So you have to change your notion of vacuum continuously.
So at a given time, there is a unique
Yes.
vacuum.
At a given time, you can define a vacuum, which is the instantaneous eigenstate of the Hamiltonian. But at dt after that time, that state will not be. So you have to adapt your notion of vacuum continuously. In summary, there is no single vacuum which is the ground state of the Hamiltonian. We cannot use this strategy to pick up one single state. And this strategy works well for at least you can be happy. Maybe you are happy having this instantaneous ground state. But in quantum field theory, this strategy will not work either.
I'm confused about that Hamiltonian. How can a term that has mismatched A and A daggers contribute to a 2-point correlation function or something like that? Like, doesn't it just annihilate the vacuum by definition?
I don't understand the question. So
Well, okay, so what we're going to do with this Hamiltonian ultimately is probably calculate a 2-point correlation function or something, right?
I mean, we don't need it. That you give me a state, and you can compute what is the expectation value of the Hamiltonian.
Right. Okay.
Or
we're
we
gonna
just
calculate
you
the
just can
expectation
add
value or something.
on the state with the Hamiltonian.
But if you want to calculate an expectation value, even,
Mhm.
if you've got mismatched if you've got an A and an A, if you've got two creation operators, an expectation value of the Hamiltonian is gonna give, since states are orthogonal, is gonna give you 0.
But depending which basis you can use. That is not completely true, because I can choose a state which is a combination of the vacuum plus one particle state.
Ah,
This is a good state, and the expectation value will not be 0 in general. I can
okay.
You are thinking on eigenstate of the number operator, but in general there are states for which that is not true.
Okay, that makes sense.
So
Can't we just have our state have what do I want to say, a time-dependent vacuum that just evolves accordingly, such that it always is?
but in general, time evolution will not bring that state. So if you want to work now in the Rodinger picture,
Yeah.
that time evolution will not bring that state to the other state.
Uh-huh.
So they are not connected by time evolution in general.
Tricky.
So you have, the notion of vacuum, the ground state changes continuously. So the message here is that no, we cannot use the Hamiltonian to single out a preferred vacuum. And I insist, in quantum field theory, not even this instantaneous vacuum is going to be available. So this strategy that we were using in time-independent situation is simply not available.
So what happens in the Schrodinger picture? What happens in the Schrodinger picture? Then we have an evolving vacuum. Or, no.
The state will evolve, but the vacuum will not evolve. So imagine that you have this definition of instantaneous vacuum, and you take one of them, and you evolve it with time. In general, it will not be mapped to the vacuum at a later time.
Because the operators are same and
Because
it will be some other state.
because that is a different state.
Yes.
So that is the same as saying that in the Heisenberg picture there is no state which is
Which is
the ground state at every time.
If we evolve only an infinitesimal amount of time forward, are the two vacuums, what do I want to say, close to each other?
That is a difficult question because what do you mean
That's
by
what we do in QFT when you are calculating and interacting some correlator and an interacting vacuum. So we assume that the next vacuum has more overlap on the ground state. I mean, and then you do some hand waving.
But questions about how close two states are in a Hilbert space are
So it
tricky because you need a measure in the Hilbert space to tell you what close means.
Maybe as a more concrete type of question, if I calculate the overlap of bra, old vacuum, ket, new vacuum at a time dt later, is that very close to being to one, or is that in general perhaps?
I mean, of course, if you take a differential amount of time, there will be
Will they be?
even proportional to dt, the result, of course. But
I hope. Okay.
But that doesn't mean anything, that doesn't solve our conceptual problem that there is no preferred vacuum state.
So what we mean here is that not only different observers will have different view about what the vacuum is, but every observer is also, for him, it like the concept of vacuum is changing with time. Is that what we mean?
No, what I meant here is just that you cannot use the Hamiltonian to solve this ambiguity that we have. So we have an ambiguity, which is we don't have a preferred notion of vacuum. And my question was, can we use the Hamiltonian to solve this ambiguity? And the answer is no.
You underlined A as in a single state.
Right.
Can I have like a small family subset of states?
No.
Oh, okay.
The best you can do here, that doesn't go to quantum field theory, is to choose a preferred vacuum at a given time.
No.
So, and you may be happy with that because that is not trivial. At a given time, yes, I could say no. Now, I know what I mean by ground state. The only thing is that state in 1 second will not be a ground state anymore. So we have something, but doesn't solve at all our problem, and in addition, doesn't translate unambiguously to quantum field theory, as we will maybe discuss. Okay. Third comment I want to make. This is just this assignment. Quantizations obtained from two choices of positive norm basis. Phi 1 and phi 2. The nice thing of the harmonic oscillator is that the positive norm subspace is one dimensional, so I only need one element. So I have two different choices that differ in a phase, in a phase factor, so phi 1 is equal to E, or I'm choosing phi 2, the solution phi 2, just a phase times the solution by 1 are indistinguishable. This is the statement. Does it sound natural for you? So the point is that this is the case because in this case alpha is just a phase and beta is 0, therefore the annihilation operators are proportional to each other and therefore the vacuum 1 is equal to the vacuum 2. So a phase doesn't spoil our quantitative, we get exactly the same. So
This is like global phase, right?
sorry?
This is like global phase.
But I want to say more than that. Maybe in this one-dimensional situation, you know, everything is too trivial. But the message here, so what I want to communicate here, that in this situation is too trivial that maybe it's not appreciated, is that vacuum, vacua, so the choice of vacuum, and as we have discussed, and therefore the choice of vacuum implies the choice of one particle state, of one particle Hilbert space, the choice of one particle Hilbert space and Fock space. The choice of our quantum theory is in 1-to-1 correspondence with the split S as a sum of some positive north subspace and negative north subspace. No matter which basis we choose in S plus. So what I want to communicate here is that, you know, so far I was talking a lot about basis, and you know, every person who is a bit geometrical doesn't like to talk about basis. So the statement here is that the vacuum and the quantization that we choose, so one particle Hilbert space and Fock space, doesn't really depend on which basis you choose. Really depends on how you split this space in a positive and negative space. If you choose two different bases here, this is what I am doing here, but by changing the phase, choosing two different bases with norm equal 1, the vacuum is exactly the same. Here is too trivial because this guy is one-dimensional. So if I want to choose two different bases of normalized modes, the only freedom I have is to change it by a basis. But if I had two harmonic oscillators, or if I have more degrees of freedom, there are infinitely many bases for this guy. You know, just rotate the bases. The statement is that with all of them, you get exactly the same quantum theory. The quantum theory is not based on the basis, but it's based on this splitting. There is a one-to-one correspondence between how you separate this space in positive and negative norm and quantizations, quantum representations of the theory. And this is basis-dependent state, basis-independent state. So, choices, different ways of split this element in a positive norm and a negative norm are in one-to-one correspondence with quantizations, quantum representations. And with representations, I mean a Hilbert space, a vacuum, creation, annihilation operators, notion of quanta, etc. this is a basis independent thing. Which basis you use inside this splitting, you can choose the one that you want. You will get to the same vacuum, to the same quantum theory. Of course, I introduce it, I got to this point using basis, but now what I want is to step back and get perspective and tell you that this splitting is really what defines which vacuum and which quantum theory you are obtaining. And is that fine? And as we will see in chapter, I don't know, later on, there is a very nice mathematical way of characterizing in a precise way how many ways of splitting this space you have. And we will see that there is a one-to-one correspondence between complex structures in the phase space and splitting. So a complex structure in the space of solutions is the mathematical object that really characterizes a splitting in a basis independent way. But I will explain that later.
So that split actually reduces to the number of ways in which we can choose alpha and beta, such that mod alpha square minus mod beta square is 1. Isn't that right? So
exactly.
Isn't that infinite? No?
Right. You have infinitely many ways of doing this.
In the split.
So
right.
Equal in one-to-one correspond like equal for them. Right?
So for each of them, you have a quantum representation.
Oh,
You choose a different one, you have a different quantum representation.
So what was the last statement?
That there is a mathematically precise way of characterizing how many different splittings there are. There are infinitely many, but they are characterized by an object that is called a complex structure. So if you want a complex structure, in this is nothing. But what I want to say is that if you give me alpha and beta, this doesn't characterize completely the splitting, because I can put a phase here and a phase here, and the splitting is invariant. So still there are infinitely many alphas and betas. So the really geometrical way of characterizing the freedom that we have in the quantization is this splitting. And there is a mathematically precise way of characterizing that by an object that we call complex structure. So the statement here is that no matter which basis you use inside a splash, you will get the same quantity. The important thing is splitting. Where I am now. Last comment is about being a bit more picky with notation. So if you see in this course, I am moving from being pedagogical and therefore omitting some mathematical details, and after I communicate the physics, then I can step back and provide more technical details. So let me provide now some. So now I want to make the statement that we have been a bit sloppy with notation. The notation I have used is quite standard in quantum field theory textbooks, but just want to make the point that notation is sloppy. For instance, we have used the same name for two different objects. For instance, we have used the name X operator as a function of time for these two objects. In our example of two different quantizations, I have represented the X operator in this way. So this is, and I have represented the field operator in this way. This is okay if you know what you are doing, but it is important to have clarity about what one is doing. So, do you think?
Is that supposed to be phi 2 star on both the A and A data term on the segment version?
Phi 2 star, yeah. So, do you guess why I say that they are different objects?
so it'd do the same thing if you act on one state, each of them, right? Because the A2 and the A1 are going to act differently on a state in some basis.
Right, but you can think that like these guys are different, but these guys are also different, so they compensate each other, and so it's the same operator. No.
But last time we used this, equated these two.
Right,
To get
right.
something, right?
Right, and that was right, because there was something implicit there, and this is what I want to point out. So what I want to say is that this is a representation. I don't have space to write it, but this is a representation of the X operator in the focus space 1. And this is a representation of the F operator in the phase space, in the focus space 2. So they are really operators on different spaces.
Wait, so they're not in S, they're not in the solution space, they're in the Fock space?
These are quantum operators. Remember that you
okay.
start with the solution space, and from here you construct the focus space, and then
Okay.
the operators act on the focus space.
Mm-hmm.
So these operators, because they are already operators, they act on the focus space. But this guy lives in a focus space, and this guy lives in a different focus space. So we cannot equate or use the same name for objects which live in different spaces. So this is just sloppy. Of course, the two focus spaces we show they are unitary related. So but one has to make clear what one is doing. So
So like expectation of X will be same for both. X acting on just one state will be different than X acting for the
no,
second.
what I mean is that you have a focus space. Focus space is a vector space,
Yeah.
and this is an operator living on that,
Yeah.
and this is an operator living in a different vector space.
Yeah.
So they are really different animals.
Yeah.
You know how to relate them because we know that there is a unitary operator that takes F1 and F2. So let me give you the solution and we will see more clearly what I mean. So it is more convenient, if you want to be more precise, to use the name X like this without anything for what I call the abstract operator. So what do I mean by an abstract operator? An operator has already the name that it operates in something. So our operator, in principle, is associated to the space in which it operates. But you can step back mathematically and characterize an operator by just its algebraic properties, without having a space where to act. Just mathematically, it's an object which you can sum two of them, you can multiply, there is another object called P, and they commute with canonical commutation relations. This is what means an abstract operator. So that is
Like observables, like in simple quantum mechanics, these observables are basis independent. So
right, for instance, the angular momentum, you characterize the angular momentum by the commutation relations,
yeah.
even if you don't have a Hilbert space where to act. So you can characterize these objects as just by the algebraic properties.
They have the same algebra in F1 and F2.
So what I do is I step back, I have Hilbert spaces here, but I step back, I have the operators abstractly defined. They are just characterized by the abstract properties, by the algebraic properties, and then I can represent them in different Hilbert states using a representation. So I want to make difference between both cases.
I feel the need to be somewhat picky here because F1 and F2 are indeed distinct, but I'm not sure if they're completely orthogonal to each other in any sense. So it's completely okay to have one element be in F1 and in F2. So
Let me finish and then.
So I'm just saying X can still be well defined while being an element of Fock space 1 and Fock space 2, right?
They are different spaces, so you cannot equate. Let me finish and probably will clarify your points, or you can ask more once I write it.
Okay.
So what I say is that first of all, it is more convenient to use the name X for the abstract operator, and what I mean by abstract operator is the object X and also P characterize the rise. Probably I need to write bigger, isn't it? characterized by its algebraic properties. They are sum, product by scalars, product between them, and commutation relations. Commutation relations. So we know that this, mathematically we can go over the details, that it fully characterizes the algebra of X and P, and that is called the Heisenberg algebra, and it's characterized by the commutation relations. So now for the representations of X and also of P, let me just write it for X, on a given Fock space, F, we normally use R on F of the operator X. So these equations that I give the number 12 and 13, if I am keeping the numbers okay. 12 and 13 are just two different representations of the X operator, one in the space F1, one in the space F2. So they really live in different spaces. They come from the same abstract operator, but they have different representations. Of course, a representation is just a map between the operator and a matrix or a linear operator in the space, which satisfies the same algebraic properties. So representations satisfy the same commutation relations as the abstract operator. But now we can relate both. So additionally, we can relate. This is why, many times they say quantum representations, because what we build is really a quantum. Additionally, we can relate both quantum theories or quantum representations by by unitary map. You have F1, you have F2. In maths, it's always the same. I am repeating what I said last day. Every time you are working with some spaces which have some mathematical properties, the relation between them are always isomorphisms. And isomorphism is a map that preserves the structure that you have. If you have, if you have two sets, you have a bilinear map, a map that goes there and has inverse. If you have two differential manifolds, you have diffeomorphisms. That is the isomorphism that preserves the structure. Here we have two Fock spaces. They are vector spaces with a Hermitian inner product, so we need maps that preserve the structure. They are precisely unitary operators. Remember, a unitary operator is an operator that preserves the inner product, preserves the normal state. So we need a unitary operator from 1 to 2. We already mentioned last day that they exist. Therefore, with this unitary operator, we can relate objects here and objects here. So we can take the operator A1, we can evolve it, and this is an operator defines an operator in the Fock space F2, because U goes from 1 to 2, so U minus 1 goes from 2 to 1. So all this guy takes an element from here, bring it here, acts with A1, and bring it back to F2. So this is an operator on H2, and what we know is that this operator is precisely this one. So this is the more precise way of writing the relation. Last day I was omitting u and un. But that is a bit sloppy. Mathematically, this is more correct. At the practical level, I will omit them, but just want you to know that if you want to be more systematic, that should be there.
That's what you were doing with matrices yesterday, right?
Sorry?
That's what you were doing with matrices yesterday, right?
I was doing that implicitly. I never said that. No, even with matrices, I didn't wrote this, and that should be there because this guy is an operator here. So an operator here can never be equal to an operator here. You need some map to go from one to the other. And also, if I add with u on the vacuum one, what I get is what I was writing this normalization factor, e to the minus 1/2 beta star alpha a dagger 2 a dagger 2 over h bar acting on the vacuum q. Last day I didn't write u, but you need a u. You cannot equate the states living in different Fock space. And also the relation between the representation 1 and the representation 2 of the x operator is also via this unitary. So this is the more systematic way of writing the relations. So this now makes sense. You have an operator in F2, you have an operator in F1, but with this U, this becomes that. Normally we never write the U's, but they are important. And in particular, they are important in quantum field theory in curved spacetimes, because sometimes that U is not even defined. So if we don't write them, we never even wonder if they are defined. So it's important to know that is there.
So what space does X as the abstract operator live in?
In any space, no space.
Okay.
So abstract operator, what I mean is the objects characterized, I didn't finish the sentence, but what I mean is that characterized by the algebraic properties without any space where to act on.
Okay.
So just defined by their algebraic properties, like the angular momentum commutation relations. Any set of operators which satisfy that computation relations, you call them angular momentum, even though you don't have any Hilbert space to act in. So a different question is how you represent them.
So I'm just curious if they don't have a space, but I'm going to pick out some x hat, and I want it to be position. I don't necessarily know where my position thing is coming from, in a sense.
Yes, because you know it, because I was not defining it, but this is what you mean by representation.
Yeah.
So a representation is a map from the operators to linear operators in the Hilbert space, which preserve all the algebraic structures.
Okay. So
the computation relation of this guy with the representation of the P operator, the computation relations have to be
So x hat and p hat living in their own space just have those algebraic properties.
And they define
that's
the operator. These are the defining properties
the totality of what they are.
And now you represent them in a Hilbert space.
Okay, and I do that through my representation map.
Right.
You generally use a representation to even define the algebraic relations.
No,
Otherwise, how we specify it?
But
just in operative form.
Right, this is the point, that normally we learn about the computation relations in a given representation. But mathematically, you can go a step before and just characterize the objects by the algebraic properties. This is really what characterizes this Heisenberg algebra, X and P algebra. You don't need anything else. A representation is something else. So normally we don't see that. We start with representation. But I am communicating that you should step back and realize the difference between abstract operators and representation.
The algebra that X hat is coming from, you said, was the Heisenberg algebra?
Yes.
Okay.
It comes from the canonical classical theory that the X and P Poisson bracket is whatever. So then you go to the quantum theory and you say, okay, X and P are going to be operators. Where? Operators satisfying these properties. These properties fully characterize my set of operators. And now I'm going to represent them in different Hilbert spaces. let me move because is that clear? So I just wanted to make a comment on this. So third section, spontaneous, and from now on I will forget again about the use, but now you know that what we are doing. And stimulated creation of quanta. This section could be, well, an example of what we have done. There is no new physical principle or mathematical structure introduced here. Just an application of what we have done so far. So I want to do the same exercise of having two different representations, but now in a concrete situation. And so consider the following form of the time-dependent frequency. So we have an harmonic oscillator with a time-dependent frequency, and I want you to consider that t is constant plus b hyperbolic tangent of another constant times t, where a, b, and rho are real constants. This example is adapted from the book of Pirrell and Davies that they have for field theory. But I think it's a very cute example, so I have adapted it to the case of the harmonic oscillator. So this is the situation I want to consider in this. Why this is interesting? Because if you plot omega as a function of time, this goes from a minus b to a plus b, and that frequency becomes constant in the past. It grows and goes to a constant in the future. So what I mean here is that this particular omega is asymptotically constant in the past and future. So omega of t so let me call omega in and omega out the limit when t goes to minus infinity of omega of t, and the limit when omega goes to plus infinity, and this is just a minus b, and this is just a plus b. And this is a quite interesting situation, because omega is time dependent, but it goes to a constant in the past, it goes to a constant in the future, and you will see that is. So the statement here is that our system is not invariant under time translation. It's time dependent, so we don't have a global time translation symmetry. But we have kind of that symmetry in the two asymptotic regions. In the past, it becomes a constant, so you recover that symmetry in the past, and in the future, you recover that symmetry again. So we can use these properties to define two preferred quantizations. So two. So I'm going to take advantage of the past symmetry, future symmetry, to define two preferred quantities.
Did you misspell two?
It was corrected before. I mean, you have already written to.
Say it again.
The underline 2 should be TO.
Thank you. So one is what we call the in representation, which is associated to the symmetry in the past. And the other is the out representation. As I have explained, our representation is characterized by a splitting of the space of complex solutions in S plus and S minus. So can you get which splitting? How to characterize the in splitting? So I'm going to have an in splitting and an out one.
The time independent harmonic oscillator with that omega n.
But that is not a solution of the space of solution, because globally there are no solutions with positive frequency.
But in the asymptotic, when t goes to minus infinity, it should be.
So it's suggesting look for those solutions which in the past become positive frequency nodes. So where S, our positive frequency subspace, S in is spanned by a solution, let me call it in, using sub index, in of t, such that when you go, the limit of in when t goes to minus infinity is e to the minus I omega in t divided by 2 omega in m. There is only one solution like that. Go to the past, give initial data by this form, evolve it, and that is the solution that you obtain. This is positive frequency in the past, so it has norm equal 1. The norm is preserved. It's going to have norm equal 1 everywhere. So it really defines for me this splitting, where the basis of S minus in is just the complex conjugated. Let me write for you what is that solution. There is an analytical form of a solution with these asymptotic properties. It's not very nice, but there is an analytical form. This is why I am choosing this example, because there are analytical solutions. So they are the mode in is the following. 1 over root square of 2 pi omega in, now a phase which is minus I omega plus, that I will define in a second, minus I omega minus over rho times the log of 2 hyperbolic cos of rho t times, of course, any respectable function needs to contain a hypergeometric function on it. I omega minus divided by rho, comma, I omega minus divided by rho. 1 minus I omega in divided by rho, comma, 1/2 1 plus hyperbolic tangent of rho.
So all of that's in the exponent, or
Only
where does the exponent?
The exponent
It's just up there.
is
Okay.
just from here to here.
Okay.
Then I am multiplying.
Is that 2 pi omega in the denominator?
2 pi omega in
What
the
happened?
denominator.
What happened to the mass?
Oh, the mass. Right. Thank you.
Okay, here's two.
With omega plus minus, they are just the 1/2 of omega out plus minus omega n. It's okay? That's
Yeah, what is the name of that function?
hypergeometric functions. There are many hypergeometric functions. This one has 4 entries, 1 comma, and sorry, there is another comma here. Dot comma. And this, this is the standard notation that you find in Mathematica. They have some specific meaning.
Is that log under the omega minus?
No,
omega
it's
seven?
multiplied.
Okay, that's cool.
So the statement is that these are the analytical solutions, which are solutions of the wave equation, which are asymptotically positive frequency modes in the past.
Here, right hand side should be independent of t, right?
Okay. No, this is an asymptotic behavior, so it depends on t. But it's only on the asymptotic past. It's not a single value. It's that the function behaves like that asymptotically in the past. Of course, you will have corrections 1 over time or whatever.
And we are finding this by taking limit t equal to t tending to minus infinity, right?
Right.
So how is t getting on right hand?
Because this is, again, if you want, I can use this symbol, which is more precise. But the function behaves like that when very early times. Mathematically, you will have times of higher order corrections that decay faster than some power or whatever.
So this has been obtained by taking this as initial condition
Exactly.
and evolving this in future.
Yes. The way that you evolve, that you will get this is always take any independent 2 solutions of the wave equation. They form a basis. So any solution is going to be a linear combination. Now take the asymptotic form of these functions when t goes to infinity and see which coefficients you have to use to get the exponential. This is quite standard. So therefore we have these modes, the mode in, and therefore we have a quantizator. We can define the A in operator, which are going to be, so we can define the A in operators, which are going to be, as usual, the inner product of these modes and the X operator, and just all the theory that we have constructed. We have a vacuum state, the in vacuum state. We have a 1 particle in Hilbert space, and we have the in Fourier space. So we have a quantum theory with this. But we also have the symmetry in the future. So we can, the system tells us that there is another preferred representation, which is called the out representation. So the out representation is based on a splitting of this guy out, and I'm going to give the splitting using a basis. Of course, the basis characterizes the splitting, but there are many bases for the same splitting. This is the point that I raised before.
Should that x hat be a representation of some x hat?
Yes, but
Okay.
I said that normally we omit just in order to avoid R of F of X. So when it's not important or very relevant, I omit it. Later in the course, I will rewrite that. I just wanted to raise the point that you know that what we really mean by this is the representation of X in the A children space. So where the plus operator, as you can imagine, is spanned by the modes I'm going to call, the solutions I'm going to call phi out, such that the limit when t goes to plus infinity of this guy is a positive frequency mode with the future constant frequency, asymptotically constant frequency. again, there is an expression for phi out that, in order to write it faster, I'm going just to modify wherever I need to modify here. So the phi out, you need to put here frequency out, and then you need, this is the same, that is the same, this is minus the same, the same. You need here an out, and you need here a minus. So that is the explicit form of the out nodes. Then we can define a dag out, a out and a dag out. We can define the vacuum out, and we can construct the Hilbert space out, and we have another quantum theory. So now we have two representations. This time they are kind of preferred because we have these two asymptotic symmetries. But we don't have one, we have two. Okay? So now, we know how to relate them. We did in the previous chapter. The Bogoliubov coefficients are the key objects. So let's find them. So, relation between them. In and out quantum representations or quantum theories. So, we can construct the Bogoliubov coefficients. Where, as usual, alpha can be obtained just multiplying phi in by phi out, and beta can be obtained by minus phi in conjugated phi out. There are analytical expressions for them. Let me write them explicitly.
Maybe I'm getting a little ahead, but why are we writing phi in terms of phi out instead of the other way around if we want to look at the evolution?
Doesn't matter.
Okay.
If you do it the other way around, what you will have here will be alpha conjugated and here minus alpha, beta conjugated. So they have the same information.
Okay.
So it doesn't matter. I am writing this because it would be easier for me. But you can also call alpha to the inverse. Minus I omega in. Let me erase here so I can write bigger. So I have here a ratio of gamma functions. One is 1 minus I omega in over rho gamma out over rho divided. The expressions are not really important for the point I want to make, but it is cute that we have, for this example, analytical expressions. So I write them for you. This is the alpha. And if you compute the beta, you have something similar. This seems very complicated functions, but we have Mathematica, so Mathematica does all the dirty work for us. So these are the exact expressions for alpha and beta. It is easy to check that, of course, alpha squared minus beta squared is equal 1. I can write the squares. Let me just write beta squared. Because it has a cute form. Hyperbolic sine of pi omega plus rho divided by the product of two hyperbolic sines. This is beta squared, for instance. Alpha squared is quite similar. In fact, I wrote for you alpha squared. This is beta, and if you want to write alpha, I can do that in the same expressions. If you have alpha squared, what you have here is a plus rather than a minus, and that's all.
How do you get hyperbolic signs out of gamma functions?
Good. Thank you. Just do it, Reading mathematical square, I don't know. I get the properties of gamma functions.
Imaginary numbers in the gamma functions.
Yeah. I think it's whenever you take the extension to the complex plane, it gets weird.
So all these functions have really nice properties. Okay, so we have all the information that we need, so we are ready to make physical statements. So let me go to this side because I occupy part of the second half. And in particular, as you know, beta squared can be interpreted as the number of quanta that this vacuum has on the focus space F out. And you can say, and what? Yeah. After all, the notion of quanta is just basis dependent, so why should I care about that one vacuum has quanta on the other one? That doesn't have any physical information. That is true in general, but in this particular situation, one can make a physical picture, which I believe is physically correct. So
isn't it like what is it called? I mean, won't people check for each partition? I mean, for decomposition of S complex to S plus and S minus. So for each case, we'll have particular values of this, right?
Right. So you have infinitely many quantizations, and for each couple, you will find that one vacuum is populated in the other focus space. So why should I care about this beta square? Why? If this is just that depends on my choice of the two quantizations. So that is just.
But here we don't have infinitely many. We have two preferred.
Here we have two preferred. And therefore, because they are preferred by the asymptotic symmetries, we can provide in this situation a physical interpretation of this beta square. In general, that is just a basis dependent statement, so I wouldn't care. But in this situation, the statement is that we can make physical statement about this beta. So let me write it. So what I want to say is that the presence of the two asymptotic symmetries, asymptotic time-independent regions makes possible to interpret beta square in physical terms. So Again, in a generic situation, I don't care about beta square. That doesn't tell me anything. But in this situation, one can provide. I'm not going to write all what I'm going to say, otherwise I need half an hour. But let me just say it in words. So imagine that this harmonic oscillator is in your lab. And you go to your lab at t minus infinity, so Monday morning. And you know, at t minus infinity, your harmonic oscillator is time independent. So there is no question about what the ground state means. So you want to leave the lab for vacations, okay, I'm going to set the oscillator in the ground state. There is no doubt what the ground state means, because you are in a asymptotically time-independent region. You put it there. That is the in vacuum. You go for vacations. You come back at t plus infinity, because grad students take long vacations. And in the meanwhile, the time-dependent frequency has grown and has become stationary again. At that time, there is no doubt again about what the vacuum should be, what the ground state is. So you go to your oscillator, and you see that it's full of quanta. You left it in the ground state, you come back, and it's full of quanta. Of course, your notion of vacuum has changed in the middle, but you were in a party, so you didn't realize. So the only thing you know is that initially, it was in the ground state, no question about what ground state means, and finally, there is no question about what ground state means, and the state of the oscillator is not ground state anymore.
Well,
It is
if
still
we're
the
looking,
previous ground.
It's still the previous ground state, but the notion of ground state has changed. And now there is a well-defined ground state. Therefore, you are in all your right to say that particles have been spontaneously created from the vacuum. And this is the phenomenon of particle
so
creation.
we're still in the same state, even though.
Because we work in the Heisenberg picture. But the same happens if you work in the Schrodinger picture.
Okay.
So that doesn't change.
So over time, the one state I had is no longer to be considered the ground state or the
Exactly.
vacuum.
So what you are doing is that initially, the oscillator in the well-defined ground state is what you call the in vacuum. Finally at t plus infinity, there is a well-defined or an unambiguous notion of ground state. Which is the out vacuum. But the state in which the system is different from the vacuum at late times. In fact, the state in contains beta square quanta at late times. So physically, you are in all your right to say that quanta has been spontaneously created from the vacuum. Created out of the vacuum.
In this case, like, is my vacuum of in like a t minus infinity is eigenstate of Hamiltonian at t tending to infinity?
Of course, because there is time independent situation. So there is like in chapter 1, if you are in your lab at the time, everything is time independent. You have your Hamiltonian, you have your time translation symmetry. Of course, you don't know what is going to happen in 5 years. So you say, no, my system is time translational symmetry. I'm going to set up in the ground state, which is the eigenstate of the Hamiltonian with minimum energy. In fact, it's the only vacuum state which is invariant under the symmetry of my system. So no question what the vacuum is.
In that vacuum, I mean, like phi in is now at phi in. Phi is eigenstate of Hamiltonian at t tending to infinity.
Of course, this is what I mean. That is an eigenstate of the Hamiltonian with minimum eigenvalue.
That means
Well, not
infinity.
at plus infinity. It's not.
So you are saying at minus infinity.
No, I'm talking about at plus infinity.
No, of course not.
is it eigenstate? Like not
No,
ground state,
no.
but is it eigenstate?
No, it's not against the number operator. Remember that.
But
You
it,
know, the number operator out is A out, and the Hamiltonian, of course, at time plus infinity, the Hamiltonian is going to be H omega out, the number operator plus 1/2 of H bar out.
Is this something you can observe?
Of course.
So,
So you agree that the Hamiltonian at late times is like that, you know,
Yeah.
and well, this number operator is
You know.
this,
Yeah.
and you know, if you put the vacuum one here, the vacuum in here,
Yeah.
of course this is not, because this guy is a combination of A in and A daga in. This guy is a combination of A in and A daga in, and so whatever this is the expectation value. This is, remember,
Okay,
this is what.
expectation, yeah.
This is the expectation value of A out,
Yeah.
what I wrote before.
but it's not like it's really spontaneous because you've got a time-dependent Hamiltonian, which means you've had an energy change in the system.
I mean, spontaneous because you only had the vacuum. This is where the spontaneous comes. You are not inducing with external input. You had the vacuum. After some time, it is full of particles. And it's true that you are just, it's because the natural basis has changed. The state is the same. Your notion of quanta has changed. But at the practical level, if you go to the lab, this is physically particle creation. Mathematically, it's a change of basis. It's that the natural change of basis has changed. But in this situation, you have all the right to call this physical spontaneous creation of quanta out of the vacuum state.
But energy is not conserved, right?
Energy is not conserved in the system. Because, you know, somebody is changing the frequency, somebody is stretching your
they're inputting energy to change the frequency.
cycle, somebody is stretching your spring.
So somebody messed with your lab while you were gone.
Of course. But, you know,
It is by self. I mean, Hamiltonian is doing it, evolving itself, right?
Right.
Like no one has shown a way to
you can think that why the Hamiltonian changes. But you know, this is extremely important because this is the core of Hawking radiation, for instance. You have a star burning full, stationary. You go to the past, to the far away from the star. You are like in Minkowski space, so you have a notion of vacuum. The star collapses, a black hole forms, a horizon appears. In the future, the notion of vacuum is very different. So if the vacuum is in, if the vacuum in is expressed in the Hawking space out, it's a thermal state. So exactly the same is what is going to happen in Hawking radiation.
So is there information paradox here?
No, because there are no horizons. So here the state was pure initially, was pure finally. Was, of course, finally is an exponential of two particle states, which is complicated, but this is still a pure state. And I don't know, I need 5 more minutes to finish the chapter. There are two things I want to say. Well, maybe I can say one thing and let the other one for me say. Let me say one quickly. I have a slide, but maybe I can say it once. So, the first person who had the intuition about this, I mean, he didn't write equations like this, alpha and beta at all, but he had an amazing intuition, was Schrödinger, in 1939. He has a paper. I don't remember the journal. And what he says, you know, he was realizing that, you know, if you put an harmonic oscillator or a quantum particle satisfying the Schrödinger equation, he was using the relativistic Schrödinger equation. But he was imagining, you know, a quantum particle, not a field. Field theory was getting formulated at the time. A quantum particle, which is like an harmonic oscillator in an expanding universe. He knew that the universe was expanding. You know, if the universe is expanding, the natural frequency of oscillation of the particles is going to change. So he thought, come on. I know that particles are associated with positive frequency solutions of my equation. But if the frequency is time dependent, initial positive frequency solutions are going to be a combination of final positive and negative frequency solutions. And that is going to mean that particles would be created from the vacuum. So he writes explicitly, this mixing of positive and negative frequency solution by the expansion is extremely important, because that physically would mean that particles can be created in pairs just by the expansion of the universe. And he wrote something like, I have a slide, maybe next day I can show it to you, with where he says that. He said, this is a phenomenon of extremely importance, because in the early universe the expansion was very violent, a lot of particles could be created, and that can have cosmological consequences. And this is precisely what happens. The way inflation works is precisely very similar to that. Of course, he didn't have quantum field theory, and his paper was completely forgotten. And 30 years later, Leonard Parker formulated the same idea independently of Schrödinger, so he claims that he didn't know the paper of Schrödinger. But even if he knew, doesn't matter, because he was using quantum field theory and formalizing everything and showing something very similar to what we have done here. A universe which is not expanding, expands, and then not expanding again. So in vacuum, out vacuum, particles created exactly this way. So the intuition of Schrödinger was just quite impressive. And so that is a very important historical notion. These genius people have an amazing intuition.
Like for path integral, Dirac had intuition and then Feynman work on it, right?
Right. Dirac also had a very beautiful intuition. And if you give me 2 minutes, I will finish the chapter.
Okay.
Okay?
Yeah.
Because otherwise next day I have to summarize everything and it will take me 15 minutes. And it's nice because I'm going to finish this talking about stimulated creation of quanta. Stay brief. So, stimulated creation of quanta. Same section, just a subsection. So you can imagine what is the question. What happens if the initial state is not the vacuum but has some in quanta? So what does it happen if the initial state is an excited in state? Question. So for simplicity, let's take a state which is, a state with n quanta. So I get a state of the in number operator. I can choose combination, linear combinations, but just for simplicity, let me consider a state with n in quanta, n factorial power n on the in vacuum. And so you set that in your lab. This is what we call a state with n in quanta. You add n times with the creation operator on the in vacuum.
You just have n factorial to the n. You have the n factorial inside the, yeah.
This is just coherent displacement.
It's not a coherent state, it's just a state with n quanta, what we have been calling n. And now you set up your lab. Rather than leaving and leaving the oscillator in the vacuum, it has n oscillations, n quanta on it. And you come back after your vacations and you measure what is going on. So what is going on is that you are going to find that, so the question that you want to ask is how many quanta, late quanta, is this initial state going to have? So this is what we have to compute. Before I was putting the vacuum here, now I am putting an excited state here. So what is going to be the result? The computation is straightforward. So in case you didn't have plans for the Mardi Gras, you can do this exercise. I mean, it's just 2 lines. It is really hard. So if you do it, you are going to get n, number of initial quanta, plus beta squared 1 plus 2n. Or if you want, I can put the 2 outside, and have here n plus 1/2.
Is that n2 beta squared?
Plus 2 beta squared times n. And this is what I wanted to compute. Just let me interpret it, and that's all. So the first term is n. So what we had initially, we had finally. So quanta initially present. Nothing happened with this guy. We had n initially, now we had n. Quanta initially present. This guy here is multiplied by beta. This is precisely the particle creation we were observing before. So this is independent of n. So this is spontaneous creation of quanta. Creation of quanta. This is exactly what we had before. But now we have a new term. A new term which is multiplied by the amplification coefficient, because this is the guy who is producing the amplification of vacuum fluctuations, and is proportional to the initial number of quanta. So this is what in quantum mechanics we call stimulated creation. So the statement here is quite beautiful. That more quanta are created just because we have particle initially present. So this is like a laser. You put some quanta and more quanta are amplified just because we have particle initially present. And the amplification factor is the same as for vacuum fluctuations. So if there is, and if there is no stimulated creation, we would have only this end, not this end here. But we have something additional, some amplification of the particles initially present. So this is and we know that in quantum mechanics, every time we find spontaneous something, we have stimulated something. So the statement here is that in this case, there is also this simulated particle creation. So, stimulated creation of quanta. This also happens in cosmology with fields, in black holes. In addition to Hawking radiation, if you throw particles, they are going to get stimulated. The black hole is like a laser that creates more, precisely because of this effect. So here, questions?
So
Are general questions or about this?
about this.
Okay, so let me summarize. And so here I want to close this chapter, harmonic oscillator, and next day we'll start with quantum field theory in core spacetimes. But it's going to be putting integrals in what we have done here. Yes, integrals of k. We have many oscillators, but there will be new effects, but the essence is already here. The mathematical concepts are already here. The physical concepts are already here. So if you understand the chapter, you will understand easily quantum field theory in core spacetimes. So if you're in a hurry, you can leave.
So this effect, the spontaneous creation of quanta. So like mathematically we see that this happens, but like how can we say with confidence that it's a physical phenomenon?
So this is let me repeat what I said before. So if you don't have any symmetry, then as I said, this beta doesn't mean anything. You choose a basis randomly, I choose a different one. Your vacuum is not the vacuum for me, but who cares? This is just a choice. But here we have really physical asymptotical symmetry. So there is a well-defined notion of quanta initially, well-defined finally. So repeat the experience that I said. Go to your lab, put it in the vacuum, come later and make sure that it's full of quanta. Who is going to deny that particles have been created? You will go there. Look at the oscillator is full of quanta. Physical is the correct interpretation. So
beyond the math we just did, this is something that we do see and observe as well.
Right, and and because there is a preferred notion of quanta initially and finally,
But
that
I have another question there. Is there physically any such system which has omega t dependence like this without any external input? you just leave the system and it has the omega, which is asymptotically. Like
Imagine that for some weird reason you decide to work in loop quantum cosmology, and the universe bounces. And imagine that there is no cosmological constant. The universe is Minkowski asymptotically in the past, Minkowski asymptotically in the future. In the middle there are galaxies, there are humans, there are grad students and quantum field theory lectures. But asymptotically in the past and in the future, you are Minkowski. You have an oscillator. The oscillator is going to be static in the initial state, static in the final time. So in the middle is going to change. So you are going to have that.
And this happens in atomic spectroscopy or something like that, distributed and spontaneous.
Right, I mean, that happens, but he's talking about this particle creation. This spontaneous and stimulated happens everywhere, but this stimulate this creation of quanta from the light.
Like apart from hypothetical cases,
Right.
is there any concrete example of this? Like
The bounce, for instance, is something very similar to this.
but
Very
it's
similar to
not
this.
like the bounce itself is a mathematical thing. It's not.
Come on. Don't say that now.
Yeah.
People are living. Our future depends on that.
Not going to be a lab back in there.
Don't say that to Parag. You're going to be in trouble.
That's what I'm saying it to you.
No, for instance, part of my work is to show that the bounce can produce some effects in the CMB, and it's precisely because of that.
That we can
Fourier modes that we see today, they were like in Minkowski before the bounce, like in Minkowski after the bounce, they cross the curvature, they feel that the spacetime is expanding, and you get this kind of effect. So. But of course, if you tell me that omega is arbitrary, time dependent, then talking about quanta, I don't even want to listen about particles. All questions that you find in books and in discussions about particles in a generic time dependent situation, for me are meaningless, because the notion of quanta is completely basis dependent. Unless you have some asymptotic symmetries. Then you can talk about, compare both notions. This is what we are doing here. But in a generic situation, all these discussions that you find in books about quanta for me are empty.
Well, the part that I find somewhat, I just want to say,
Sorry,
troubling.
so let me add something. Except, for instance, here in the Earth, the curvature is so low, and these distances are so low as compared to the curvature of the universe, that here it makes sense to talk about quanta. So in this situation, it makes sense. What I mean is that in cosmology, when you are doing cosmology or physics where the metric, the curvature changes with time, there the notion of particle is completely ambiguous. Talking about particles close to the horizon of a black hole, which is forming, that is completely empty, because in that situation, the notion of quanta is ambiguous.
Besides special cases where I have asymptotic symmetries and negative infinity time and positive infinity time, in my general case, it doesn't seem like you can make any physical predictions.
Right, this is what I am saying.
Okay.
In a
that's-
generic time-dependent situation, the notion of quanta and vacuum is basis dependent. So
Okay.
they don't have physical reality. All the discussions that you want to make are kind of empty. So talk about explanation values of
Yeah.
operators like energy momentum, 2-point functions. That is well defined. But there is 3 particles rather than 2. Who cares? What do you mean by particle?
Expectation or Hamiltonian, like number operator.
Number operator has to do with quanta. But Hamiltonian, no. Hamiltonian is an operator, which is defined independently of any basis that you want to use.
If we start with the n particles, why is it that it always increases?
That is a very good question. No, it can also decrease. So
But this equation seems to us everything is positive.
right, because I was choosing a very particular initial state. So of course, look at that. The initial state was the vacuum. I mean,
If it's vacuum, then it's fine because you can't decrease further.
right, but the vacuum goes to a very complicated state.
Yes.
If you now reverse the situation, if you start with this very complicated state, you will get the vacuum. But you have to prepare this extremely fine-tuned state, which is vacuum, 2 particles, 4 particles, with the right coefficients. And in that case, you will have particle destruction. So it is completely true that because the equations are time symmetrical, if there is particle creation, there is particle destruction. But the statement is that to get destruction, you need to fine-tune the state initially. But But of course, it's mathematically possible. In most situations, you have particle creation because you choose a random initial state, but you can have also particle destruction.
So is the
It's a very
fact
good
that we,
question. Sorry?
is the fact that we see particles an effect of fine tuning?
No. Here we see particles, and we can define particles, and people talk about particles in labs because, as I said, the curvature of the space-time is much, infrared as compared to our modes here. So here there is a well-defined notion of particle. I know what I mean by a photon. And it's extremely useful to talk about quanta when the notion is available. But conceptually, one has to understand that the notion of that, in general, is ambiguous. Is basis dependent.
Well, that's somewhat discomforting because it seems like most of my physical predictions have no generality.
But you have to learn to do field theory. It's not a theory of particles, it's a theory of fields. And then you can compute expectation values of fields, of momentum.
Oh, tricky. So when we jump to field theory, maybe this kind of, we're going to say, I guess, remedied in some sort of way.
Right. You learn that a field theory is not a particle theory. It's a field theory. You can completely, rigorously define it and do predictions and do computations. And this is what we do in cosmology.
Okay.
We take initial state, we compute the tubing functions. You want to talk about particles, you can talk about whatever you want. But what I see in the CMB is two-point function, and that is independent of any convention about quanta that you want to make. I don't need to define particles to make predictions.
Interesting.
The same for Hawking radiation. You can talk about quanta initially and finally, but unambiguously you can talk about the two-point function initially. I know what means two-point function of the vacuum, and I know what means the two-point function of a thermal state finally. And I don't need to define quanta to make predictions in field theory. We are jumping already to field theory.
Okay, but that's very cool. Or if you take one very specific moment exactly in time, you can have well-defined particles.
Right.
But that's still not.
Or you are in some situations like here in Earth, where the curvature is so low that there is a well-defined notion of quanta. So here it makes sense. But when we talk about black holes, cosmology, then one has to learn that that notion is basis dependent.
Oh,
It doesn't have
sure.
physical reality by itself.
Because, yeah.
Any question, Perisite?
There's only two of them left.
Any question?
Nope. Nope.